Hello, everyone. My name is Ross Signal. I'm the Director of Product Management and Marketing at Dranitz. Thank you for joining us for Module 4 of our virtual power monitoring seminars. Today's topic is going to be on harmonics. And let me just change the screen here, and we will show you today's agenda. So we're going to be talking about harmonics. We'll skip to the second bullet first. What are harmonics? Why are we concerned about harmonics? What are the standards in harmonics? I know we have an international audience here today. So we'll focus on, what are the IEC standards, because they're kind of a baseline for what the IEEE has done as well on harmonics. So we'll speak about both of those and maybe give you some tips on which ones do you follow. And so we'll speak about that, as well as talk about how harmonics are properly recorded by the instruments, measured and recorded. There are differences, and the differences really have to follow, or the differences between instruments may be on manufacturer's implementation, but we boil down to these standards. And if you're in compliance with these standards, it dictates how to properly record these things. We're going to give you some other information on triplet harmonics. Why are triplet harmonics important to understand and to know? And we'll talk about a rule of thumb on harmonics and how to get some information on whether you have an issue with harmonics and some of the basics on the rules of thumb. In our earlier web presentations, we spoke about energy efficient lighting. I think it was our second meeting on energy where we spoke about the energy savings on energy efficient lighting like LED or CF bulbs. And we've been kind of teasing you a little bit along the way on, are there any power quality issues related to that? So we're going to wind up with that as well and speak about that. We'll have some poll questions along the way. As an introduction, I did skip ahead. I'm joined in the room today by Thurman Bridgers, who you've heard on some of our other seminars here, and also Ken DeMario. They represent a major part of our technical support staff here. They are both experts on our products and experts in the field that we're discussing here today. So if you have any questions during the presentation, feel free to chat them. Use the chat feature of Zoom, please. If you chat during the presentation, we'll try to answer your question when you chat it if it's an appropriate time. However, at the end of the presentation, we'll definitely be getting to all the questions that you guys chat up. So we're happy to do that. So, and Thurman and Ken are going to help moderate those. Just a little infomercial. Our next and final web training for our summer 2020 series will be next Wednesday on the 23rd at 11 a.m. And that really pulls everything together that we spoke about in modules 1, 2, 3, and 4, wraps it up in how to do a power survey. You notice that doesn't say how to do a power quality survey, how to do an energy survey. There's a lot in common between energy monitoring and power quality monitoring. And also people do them simultaneously. So we have a whole separate module next week to wrap this seminar series up on what are the systematic steps that you want to do when you perform a power survey. And again, power quality, demand and energy, either or both are kind of wrapped in this presentation. So please join us next Wednesday at the same time. If you have not registered for next Wednesday's session, please just visit our training page on the website. Same page you registered for this session and our prior sessions, and we'd love to see you register. And we'll also send out some email reminders beginning of next week in case you haven't done it. So again, we're going to talk about harmonics today. The basic thing is chat your questions to us. And just a reminder, again, we are recording this presentation. The webcast page on our website has the recordings of our prior presentations, and we'll have this presentation posted, or the recording of this presentation posted probably towards the end of the week. So for those of you who are new to us, who haven't joined us on our prior presentations, just a little bit about Dranitz. We are located in Edison, New Jersey. It's a convenient town, named after Thomas Edison. But we are stone's throw from New York City. This is Lower Manhattan over here. We are less than an hour train ride, 45, 50-minute train ride into Manhattan, a very good location. And of course, the pre-COVID times, we had a lot of customers visiting when they're in town, visiting New York City or whatever on their personal time, their vacations or on business. We love to see you at our factory once we can, accept people again post-COVID. So that's our location. Just a few words about our products and service portfolio. We are the manufacturer of three-phase power quality, demand, and energy instruments. We just introduced a new product called Dran Expert, which is an energy instrument that also has basic PQ detection capabilities. We'll briefly touch on that in a few minutes. We also manufacture permanently installed power quality demand and energy instruments. These are fixed systems. They're installed in substations and remotely accessed via our software. So we have application software and system software for both our portable tools, which is mostly our DranView software, and our fixed system tools, which is mostly our PQView DE or full PQView software, which works very well with our portable instrumentation, and quite candidly, PQView works very well with a lot of other instrumentation out there, also from our competitors as well. We are owned by a company called Gaussen Metrowatt. We are the U.S. master distributor, or North American master distributor more appropriately, for the Gaussen Metrowatt products. They manufacture precision multimeters and testers, electrical safety testers, insulation testers, installation testers, and other types of handheld testers, as well as we have another sister company that offers light meters. It's a company called Gaussen Photo. So if you see us promoting and selling Gaussen Metrowatt products, it's right out of our facility here in New Jersey. So for Dranitz, one of the things we pride ourselves on is our free technical support. That's Ken and Thurman here joining me in the room, as well as our other support staff, myself, and even our developers are happy to speak to you about our products and help you through any questions that you have pre-sale, but certainly post-sale, to make sure that you get the most out of your products and they're problem free. So feel free to drop us a note, send an inquiry on our website, email us, call us, send up a smoke signal. We're happy to talk to you about the products. However, there does come a time where we get beyond the free technical support, but we also offer paid, what used to be on-site support, and hopefully will soon again remain or continue to be on-site support for product commissioning and product training for the product. So these are actually classes which we now do remotely via Zoom or any tool that you prefer on how to set up the instruments properly, make sure they're properly connected, make sure they're configured properly, working on your networks, but also operational training. And this applies to our portable instruments as well as our fixed systems. So we want to make sure you get the most out of your product, and sometimes that means we'll give you a little class on how to use them. And not only how to use them as far as we're concerned, but it's based upon your application. What are the important things based upon how you are going to use these products? Of course, visit our website. If you're here at this meeting, you probably have done so already to register. Our website is a library of educational materials, case studies, tips, and product information. So feel free to go visit it. Of course, researching our products, but also to educate you. And as I said before, the recordings of these presentations are also available on our webcast page. Just a statement that products designed by Dranitz, if they're designed in the building we're sitting in New Jersey, they are manufactured by us. So the second floor basically designs the instrumentation, and they're manufactured on the first floor in this building. So we're proud to say that we're made in the USA. So just to put a visual on our products, this is our portable products here, our HDPQ Plus and SP products. This is the new Dran Expert product I was referring to before. Dran Expert is a portable power energy / PQ logger. So it has a full-fledged bidirectional energy and power monitoring capabilities, but it's also a PQ detector. It'll tell you when you have RMS power quality events. Certainly not to the elaborate nature that our more expensive and more capable products have, our HDPQ Plus. So a lot of customers will use Dran Expert to detect a problem, and then maybe use one of our HDPQ Plus products to go diagnose the problem and get more details. Of course, our DranView software works along with all of our portable products. Moving on to our fixed systems, we have our HDPQ data node, our 61,000 instruments, as well as a line of AM series energy and power panel mounted meters, as well as our PQ 3K and 5K panel mounted power quality and energy meters. All work seamlessly with our PQView and our PQView DE software. Final note, when we referred to Gaussen Metrowatt products before, this is just an image of some of their products. Precision multimeters, handheld single or multi-channel multimeters, safety testers. This is a light meter. This is an industrial tester here. So a full suite of products are what's offered. Well, you didn't come here to talk about the product specifically, you came here to talk about Harmonics and hear about Harmonics. So we're going to actually start with a poll. And the first poll is really, what are Harmonics? So let's go post that poll. Let me launch the polling here. So the question is, what is a harmonic in a power system? Is it a wind instrument? Maybe not. You can use your judgment. Is it a change in fundamental frequency? Is it the integer multiple of the fundamental frequency? Or is it the AC component in a DC system? So again, we'll give you about 15 more seconds. Please answer your poll here. Okay, about 5 seconds more. We've got about almost all of you have answered. So we'll give it a couple more seconds, and we're going to cut that off at 35 seconds. So let me share the results. Most of you are correct. A harmonic is the integer multiple of the fundamental frequency. It's not a change in fundamental frequency. Of course, it's not a wind instrument. That's a harmonica. And it's not an AC component in a DC system. So thank you. Get a little participation with that. Hang on, I have to shut off, excuse me a second. I just have to shut off the poll here. So stop sharing the results. Close that. Okay, I apologize. Can one of you guys close out that poll, please, Thurman? Okay, thank you. I'm sorry about that. Okay, so harmonics. What is a harmonic? As we said, it's an integer multiple of the fundamental frequency. If you're in the United States or North America, probably most of Latin America, I believe, the fundamental frequency is 60 hertz. So that's the first harmonic. Europe, Asia, Africa, much of the rest of the world, the fundamental frequency is 50 hertz. So an integer multiple is actually 2, 3, 4, 5 times whatever that fundamental frequency is. So the second harmonic at 60 hertz is 120 hertz. At 50 hertz, it's 100 hertz. The third harmonic is 180 and 150, and so forth. So it's easier to put a picture on things. So I'm going to actually describe this picture here bottom up. And this is not a real power system. This is just something we made up for descriptive purposes here. But consider this bottom image what we call the composite waveform. If I take my HDPQ plus from Dranitz, I plug it into my 120 volt outlet here, because we are in a 60 hertz system, and I measure the harmonic content, I'm going to get a composite waveform. That's that dirty waveform, whether it be voltage or current, that has the harmonic components in it. Now, what this instrumentation does, we'll go into that detail later, it kind of peels out what frequency components are in that, much like what a spectrum analyzer would do. So in this simple case here, this composite waveform at the bottom is made up of X% of this fundamental, that's the 60 hertz component you see here, and Y% of the third harmonic, that's 180 hertz, okay? So this is a simple case, but what the instrumentation does, it takes the probably dirty composite waveform, breaks it out into its individual frequency components, the fundamental, and all the harmonics up to the capabilities of the instrument, and then presents it to you as a user. And it gives you the information to judge whether you have a harmonic issue and whether your harmonics may be in compliance with your local requirements. Maybe IEEE 519/2014 here in the United States, or an IEC 61000-3-X compliance standard in Europe, or hopefully you get the picture from it. So if I go back a slide, you can see kind of where this makes sense. So I have my composite waveform, the instrumentation peels out all these individual frequency components and presents it to you, okay? How does it present it to you? Usually one of the ways is in just a harmonic graph, just a spectrograph of what are the individual harmonics. So I'm gonna actually share another screen, and I have my DranView software here that is logged into one of our HDPQs. If I can just find it here just a second, it's right over here. And this is an HDPQ, it's an HDPQ plus actually, that's measuring the power at the service entrance of our building. So as we shared at our last presentation, the public service electric and gas is our utility here in the part of New Jersey where we reside, or where Dranitz is. And we have much instrumentation, pretty much all of our current instrumentation measuring that feed from the utility. And these are the harmonics on phase A, the spectrograph of the harmonics on phase A from the PSE&G feed. Okay, we are a light to medium manufacturing facility where we build all our products. So here's just a live feed. This is from a real instrument. You can see here's the THD up at top at 3.6%. And this is channel A. I can easily just go change the channels. I can change the parameter. I can look at phase B, phase C, the neutral phase. I can also look at the current. I could also look at the watts or power harmonics if I chose to do that. So I just figured I'd share a real-time view of that. So let me go back to our presentation. Okay, so you'll see pictures like this from the instrument. This is very easy to describe here because it's much larger here. But what you'll usually see is each individual harmonic. This is the second harmonic, the third harmonic, the fourth, the fifth. Usually this is displayed as a percent of the fundamental. So what you're seeing here is the harmonics are displayed as a percent of what it should be. The fundamental, you want 100% harmonic content in the fundamental. That means you don't have harmonics. You have a pure sine wave. That's the ideal. We know that's not really reality in what we do. So where do harmonics come from? They actually come from the loads that we plug into our systems, whether that be in a basic case, just a basic computer load, or the PLCs we're putting into our manufacturing facilities, or our control facilities, or a data center with the electronic power supplies in our servers and all our networking equipment, stuff like that. So the bottom line with harmonics is that the utilities and even our alternative energy sources, they produce very pure sine waves, almost completely pure sine waves. So the generator throws those sine waves at usually a high voltage down on the line. When we receive it, we plug in stuff and we corrupt that. So the things that we plug into our power system create the very harmonic problem that we're looking in. So harmonics just need to be managed at the facility and also at the utility level. And this is how you look at them. So again, we're looking at usually a percent of the fundamental, what it should be. And you can see here in this example, that percent is that maybe 11%. This is something called THD, total harmonic distortion. What THD is, it looks at all the components of the harmonics in a voltage or even a current waveform, and it gives you that one number to reference. So what you see to the right is each individual harmonic component, which is rolled into this one THD number. And an analogy I like to give is when I go measure the voltage in a line plug in my office here, it's 120 volts RMS. So that RMS means that's that one number I can use to reference the voltage here. Okay, so THD is very similar. It's a one number to represent all the harmonic content for voltage on that channel. In a three-phase system, it's phase one, phase two, phase three, and you have voltage and current THD. Okay, so hopefully that was clear. So really, when should you be concerned about harmonics? Well, harmonics are typically a concern, and they're considered a problem when they're always present. They're steady state distortion that's continuously occurring. Now, if you think back to our last week's presentation on power quality, well, we distorted the waveform. That's what harmonics do. They distort the waveform. But the difference is when I have a transient, excuse me, I have a sag or a dip, I have a swell, that's temporary. So yes, I distort the waveform, or the power system waveform's distorted, but it returns back to normal fairly quickly. Okay, that's not really where you're concerned about harmonics. Yes, there's harmonic content in that situation, but that's a lab exercise. Here for harmonics, you're worried about when it's continuous, like this distorted waveform you see here on the bottom. I believe this is for current. So really, harmonics are concerned when they're continuously occurring. So although any waveform can have harmonic content, we're typically concerned with the cumulative effects of the continual harmonic distortion for voltage and current. So we're looking for the effects on neutrals, on motors, on transformers, on the loads that we plug into the power system. So that's why harmonics become a management issue for the power system. So what are the standards for harmonics? And like we did with the PQ section, we're going to just get a little bit geek here. The harmonic standards, really the current harmonic standards that we use worldwide are based on IEC 61000-4-7. The IEC is an international organization, as we mentioned previously in our other seminars, Swiss-based, I believe. It's an international harmonic standard that's been used for many years, probably 15 to 20 years, but it's also part of that IEC 61000-4-30 Class A requirement that we spoke about at our last presentation on power quality. So it's been in every version of 61000-4-30, edition 1, edition 2, and now of course it remains in the current edition 3 for that. So that's been the baseline for many years on how manufacturers and how the industry is supposed to measure harmonics, okay? So IEEE 519 was updated in 2014, and now it's referenced IEEE 519 2014. And the IEEE, again, being followed in US and North America, maybe parts of Latin America. And really what they said, they didn't, prior to that date, the IEEE didn't have harmonic measurement techniques. They had compliance information in there in the 519 standard, but not the details on how you measure harmonics. And that's key. You know, prior to -4-7 and prior to the IEEE following those techniques, each manufacturer had the potential to do it different. So which one was right? So 61000-4-7 came up with the techniques which are still used today for harmonics and actually other measurements in power instruments. And the IEEE said, you know something, the international community got it right. We're going to harmonize with that. And what that means, we're going to just use the same thing. It means copy, basically, in blatant terms. So IEEE 519 2014 uses the exact same measurement techniques as IEC 61000-4-7. And we're going to actually share some of those techniques in the coming slides. So what the IEEE did is they said, okay, here's how you measure, but you know, we're going to add a couple parameters and we're going to add our own compliance limits to what the IEC has done. So the IEEE specifies 3-second harmonic calculations or measurements for voltage and current, and they're called very short time harmonics, or VST if you put it that way. Then they said we're going to look at a larger period of time or longer period of time, and they specify 10-minute harmonic calculations for voltage and current called short time harmonics. So these are this is new terminology as of IEEE 519 2014, which is about 6 years old right now. But again, they also defined limits and statistical requirements for both short time and very short time harmonics. And that's part of the compliance report. So 519 2014 defined how to measure harmonics for voltage and current. The same techniques are used for voltage and current based upon 61000-4-7, but they put compliance limits on top of that. So based upon a voltage level that you have and a current level that you have, what are the compliance limits, okay? So why are managing harmonics, and why is 519 2014 and also 61000-4-30 important, okay? Well, first of all, from a US and North American perspective, 519 2014 is the current US recommended practice for harmonics measurement and compliance, okay? Compliance limits are referenced at the point of common coupling between the utility and the end user, okay? As this last bullet says, the intent is to manage harmonics at the interface point between the utility and the system owner or the end user. It's not meant to manage utility harmonics. It's not meant to manage harmonics within a facility, although many times this standard, and it has been for years, or recommended practice has been for years, used to measure harmonics within a facility. It's really intended at that point of common coupling, which is basically the metering point where the utility gives you your power. But again, practically speaking, it's used within facilities as a reference, right? It has applications all over the place: facility management, utility management, and DER, distributed energy resource and alternative energy management, which is looking at that coupling point between the DER, the wind farm, the solar farm, whatever the alternative energy is, and the utility system. So using the same standards. In fact, we have a little bonus section here if we finish on time here, where we're going to have a little extra time to talk about some of the new standards in distributed energy resources, which overlaps to harmonics and other things. So how do we define the compliance limits for 519 2014? It's split between voltage and current. The voltage is the recommended limits for individual harmonics, and VTHD, again, that voltage total harmonic distortion, specified at various bus voltages measured at the point of common coupling. And the reason for the various bus voltages, and you'll also see that for current, is really this kind of one theory. And as I said before, that the loads that we plug into the power system are the ones that create the harmonic problems. It's the way current is drawn from all the electronic and other loads that we plug in. So harmonics are not generated from the generators of power. They're not created there. It's the consumers of power. So logically speaking, as you go up from the facilities and up the power system towards the generators, that's higher voltage. That's not where the harmonics are coming from. So as the bus voltages are higher, the acceptable limits for harmonics are lower, because logically speaking, the harmonics are not originating there. So you have lower allowable limits. So the limits are tighter, put in different terms, at the higher voltages, because we're closer to the generation source. We're in the transmission of the generation systems. That's because if you have anything from that point down in the system has to be shared by everyone connected to the system, other distribution points and any facilities or loads in the system. So conversely, as you get closer to the facilities and the producers of these harmonics, the allowable limits are higher. So as the voltage goes down, as you get closer, like in the US, to a 40 volt distribution point, or 277, or even 120, 208, your allowable limits on harmonics are raised, because that's where the harmonics are coming from. And again, we're managing it at that point of common coupling. Okay, so the acceptable limits for voltage are based on the bus voltage, again, with higher voltages having lower acceptable limits because they are farther away from the harmonic generating sources. Current, very similar sort of approach. The recommended limits for individual current harmonics are specified at those same, I think, various bus voltages, with that same concept in mind. Okay, the higher bus voltages have lower acceptable harmonic current limits. Except what's one change in 519/2014 is that TDD, total demand distortion, is referenced for harmonics, not current total harmonic distortion. And to just simply kind of refer to it as TDD, it needs to also be measured by the instrument, but it's the harmonic content based upon the capacity of the system. With the theory is, if I have a lot of rich harmonic content, but it's only on a very small current amount in a large system, making this up, if I'm consuming a half an amp in my house on very distorted current on a 20 amp circuit, that's insignificant to me. Even though making this up, 100% THD sounds bad, it's only a half an amp, so it's not a big problem. So when you take TDD, you're looking at the harmonics in relationship to the capacity of the system to judge whether it's a big problem or not just looking at THD, which just says, yes, it's distorted. So it keeps that in mind, okay? So continuing on, and I think this is the last slide on this. So the basics of how this instrumentation works, and this is very important, because you want to make sure when you're in a 519/2014 environment, or even internationally outside of the United States with 61000-4-7, that your tools are following these techniques. And a lot of tools follow these techniques that are Edition 3 Class A compliant to 61000-4-30, but those that are not compliant may or may not follow these techniques. As an example, our Dran Expert product follows these same basic techniques. It's not Class A compliant or anything close to it, but the basic techniques are based upon this. So as specified by 61000-4-30, as well as, 61000-4-7, as well as 61000-4-30, the basic unit of measurement here is a 200 millisecond window of AC cycles is captured. So that's 10 cycles at 50 hertz and 12 cycles worth of information at 60 hertz. And that's this window at the bottom. So to make it very basic, all the harmonic calculations, and in fact other calculations by our products, are done based upon this 200 millisecond window. It's not one AC cycle, it's 10 cycles at 50 hertz and 12 cycles at 60 hertz that are used as the basis for this, which rolls up into your IEC 61000-4-30 Class A Edition 3 compliance, rolls up into your IEEE 519/2014 compliance, as well as other things, okay? But be very clear that this 200 millisecond window is not, I said note, I apologize, that's a mistyping here. This does not apply to the sags, swells, transients, or other higher speed or faster power quality information that most of our instruments can record. In fact, even our new Dran Expert goes down to one AC cycle. So a power quality instrument for these types of measurements needs to be one AC cycle or even sub-cycle. I mean, our HDPQ Plus Explorer Plus goes down to, has 1 megahertz sampling, so it's much less than 1 cycle. So again, this only applies for harmonics and maybe power measurements in the instruments, watts, VA, VARs, power factor, not sag, swells, transients, and things like that. So 519, 2014 is a compliance standard as well. So basically the bottom line is it's pass fail. So here is a picture of a report for 31 days. It's a weekly test with daily reports on your very short time harmonics, okay? As well as weekly reports for your short time harmonics, okay? Again, excuse me, very short time are based upon a 3-second, short time are based upon a 10-minute interval. And this is a pass-fail report. So let me just skip over and I'll just share something in DranView, which I also have set up. And let me just share right over, oops, next one over. And this, you can see on the right-hand side here, this is a real compliance report measured in our DranView software. This is one of our engineers did for a test to test this report. So this isn't a real power system that we're reporting failure on, but it's a real test simulated in our lab so we can kind of demonstrate this. And you can see this is a pass-fail report. This is telling you in red which items have failed the report. Anything in black is fine. Anything in red has failed the compliance limits that are outlined in IEEE 519 2014. Okay, and it shows up just like an event in our DranView software. Harmonic percentage daily report. You can see me switching between them here. All right, so we're happy to answer any questions later about this as well. So continuing along. So triplet harmonics. So we've talked about the standards. We talked about how harmonics are acquired by the instrumentation. Well, what are some of the concerns about harmonics? Okay, we talk about them, but what are the dangerous harmonics, to put it in a different term? So let's go start our second poll here about triplet harmonics. So let me do this. Let me skip to the second one. I'll launch the poll. Okay, so you can see that. What are triplet harmonics? So we'll give it about 30-35 seconds to answer. So when there are 3 harmonics measured in a power system, harmonics that are a multiple of 3, or harmonics that are 3 times worse than the other harmonics. So we'll give it a couple more seconds. Okay, 20 seconds, maybe 15 seconds or so. We'll let you guys answer that. So we've got about 2/3 of you have responded. Okay. All right, we'll cut that off at 35 seconds. Let me end the polling. Let me share the results. Okay, so most of you thought that a triplet harmonic are harmonics that are a multiple of 3 in the power system. And yes, that's exactly what it is. Okay, that's exactly what harmonics are. What triplet harmonic? Okay, thank you. Okay, Thurman's going to close that out for me. For some reason, I can't close this polling. So. You got it, Thurman? Ken, can you close that out, please? Excuse me a second, guys. Okay, thank you. We got a big flat screen in the room so I can see what you guys are saying. So what are triplet harmonics? Yes, triplet harmonics are harmonics that are a multiple of 3, okay? So that's usually in most power systems. That's the 3rd, the 6th, the 9th, the 12th, the 15th, and so forth, all right? But why should you be concerned about these triplet harmonics, all right? It's because they add in the neutral, all right? Other harmonics don't add in the neutral. Triplet harmonics add in the neutral. So I'm going to give you a live view of this in a second, where we're going to actually present our harmonics demo tool that's built into the same DranView software that many of you have. But let me visually describe the issue with triplet harmonics. So this is a 3-phase system. Again, what we see is phase A, phase B, phase C, shifted by 120 degrees. So it's just a phase shifted from left to right, the same way a 3-phase system is offset by 120 degrees. So again, as we described before in one of our first slides, here's the 60 hertz fundamental, and here's the 180 hertz third harmonic. So if you're in outside the United States in a 50 hertz system, okay, maybe this is my 60 hertz fundamental, and this is a 150 hertz third harmonic. So whichever way you look at it, it's fine. But you can see the 180 hertz or 150 hertz component at 50 hertz is the first triplet harmonic. So you can see, visually follow these gray areas, they add in the neutral. So the vector sum at 60 hertz, or you could flip it to 50 hertz, is 0, but the vector sum of the third harmonic is 3 times. All right, so they add in the neutral in a Y system. So to put a picture to it, and we can actually share some information here and do some tweaking, is our Harmonics demo tool. Now, I'm not quite sure if many of you are aware of that. It's built into DranView. I believe it's in the data section. Is that it? It's in the view section, actually, of DranView. All right, go view, Harmonics demo tool, and you get what I have displayed here. So what you see here is phase A. This happens to be for voltage. Phase A, phase B, phase C, in the neutral. The neutral is hard to see because it's 0. So what this allows me to do is basically change the amplitude, or the percent of fundamental of harmonics, for the third harmonic, the fifth, the seventh, the ninth, the 11th, or the 13th odd, or the second, the fourth, or the sixth even. Okay, so I have the ability to do that, and I have the ability to see the effects on the neutral. So as an example, we said only triplet harmonics add in the neutral. So let me try something first that's not a triplet harmonic. You see, this is a fifth harmonic. So I can just click and hold here, if my computer let me do it. I've added 9%. I'll give it one more, 10% of the fifth harmonic. Now you can see A, B, and C voltage got very distorted, but look at my neutral. Nothing changed in my neutral. So if I reset this, and I now change the third harmonic, which is the first triplet, I go up to 10% of that. Look at the effects on the neutral. It adds in the neutral. So that's the effect of triplet harmonics. Now, I can do that for the next triplet harmonic, next odd triplet harmonic, which would be the ninth. Okay, you can see the effects there. Now I'll throw in some seventh, just arbitrarily. Look how much more distorted my phases A, B, and C got, but my neutral did not change. Okay. We're going to talk about even harmonics later, okay? Many people think that even harmonics cannot be triplet harmonics. Well, mathematically, yes, they can, but as we're going to speak about in a couple slides, they don't appear as often in power systems. So as an example, if I put in the second harmonic, I can do that. All right, you can see, look how distorted. This is like a slope here. This is not an AC waveform anymore, okay? But you can see these A, B, and C got distorted, but the neutral was unaffected. If I reset this, now I put in the sixth harmonic, which is the first even harmonic, even triplet. Look at the effects on the neutral, okay? So even harmonics can be triplet harmonics, but as we'll talk about in some of the coming slides, and I kind of gave away one of the questions, I think, but yes, they can appear as a triplet harmonic, but they just don't happen as often. So, that's kind of the triplet harmonics, and using the harmonic demo tool in DranView is a very good education tool for that. So let me go back to sharing our presentation. Okay, and I see our screen changed. So the rule of symmetry, and this kind of goes to the even harmonics. Let me launch poll question number 3 here. And let's talk about the rule of symmetry. All right, so let's launch polling. So true or false? Okay, this is about the rule of symmetry. Even harmonics do not appear in most properly operating power systems. So I actually gave that away before. It's kind of an open book test. So there's also a second question once you answer that, okay? If it's true, why would they not appear in a properly operating power system? So if you guys can just answer those polls. Okay, so again, the even harmonics appear in a properly operating power system, okay? Or do not appear in a properly operating power system most of the time. And if that answer is true, why don't they appear in a properly operating power system? And we'll explain that in a few minutes here, or a few seconds actually. Okay, so we're about 45. Well, this is a 2-part question, so we'll give it another couple seconds here. Okay, we'll cut it off at 55 seconds. We're at 52 here. Okay, let's look at the results here. All right, so most people got it right. Even harmonics do not appear in most properly operating power systems. Yes, that's true. They do appear. It's not like they cannot appear, but most properly operating power systems do not have even harmonics. The reason being is that rule of symmetry, and we'll explain that. Okay, that's our next thing. So we have symmetrical waveforms in most power systems. So that's the reason why. We're going to have a slide on that. So Ken, do you mind closing out that poll, please? Thank you. Okay, so this is PQ rule number 3, that even harmonics typically do not appear in a properly operating power system. Why? It's that rule of symmetry, and quite frankly, just the way the math works. Now, harmonics are usually calculated by most instrumentation by Fourier transform, which takes this dirty waveform that you see, breaks it out into little bins, what we call it, for the individual harmonics. You got X amount of harmonic content for the fundamental, the first, the second, the third, and fourth, and all that. So when the positive and negative halves are the same, only odd harmonics mathematically appear. And that's what you see here. This is a symmetrical waveform. What symmetrical means is that, yes, this whole thing is dirty, but the top half and the bottom half are symmetrical. They are the same. So if I take this bottom half and flip it over to the top half, line them back up again, they are the same. Where asymmetrical, or those that lack symmetry, the positive and negative half are different. So here's the positive half, nice and clean. The negative half, this is actually the output of a bridge rectifier, where the bottom half is not conducting, the diodes are blown. Mathematically speaking, on asymmetrical, or in this case, both even and odd harmonics will exist. Just the fact in most of the power systems, most of the loads we're plugging into our power systems, that they are symmetrical. So even though distorted, the positive and negative halves will look just about the same. Oh, they will look exactly the same. So that means you will not see any significant odd harmonics. So as a rule of thumb, if you see even harmonics and you know you have devices that should be symmetrical, then maybe there's a problem, such as the one on the right here with the asymmetrical waveform. I understand that exceptions to that rule may be some medical test equipment, understand some x-rays and other devices consume power different in the top half of the waveform than they do in the bottom half of the waveform. And that's really the difference, okay, that we're drawing energy the same on the top and bottom half of the waveform. So some cases that is different by design. So this rule of thumb will not apply to that. So, okay, continuing along. So what are the causes and effects of harmonics? You have rectified inputs and power supplies, non-symmetrical or asymmetrical current, intermittent electrical noise from loose connections. If they're continually occurring, they can be the cause. And just they're the loads in the system that are causing it in a modern system. Even going back 20 or more years, you see harmonics being an issue. And basically power systems happen to be designed in the presence of harmonics. So what are the possible effects? Overloading of neutrals, we spoke about that. Overloading of power sources, low power factor, reduced ride through. Certain loads, certain power system devices like transformers, motors, and other devices don't work well with a significant amount of harmonics. So you can overheat transformers. That's why there's K-rated transformers. They're designed to live and properly operate within the confines of the harmonics that are in the system design. If you didn't K-rate a transformer, maybe that transformer wouldn't handle it well. In worst cases, they light on fire, which there are true case studies about that. Motors, they're very interesting because motors are susceptible to harmonic problems. But also when you measure harmonics at the terminals of a motor, like a VFD or something like that, if there's a problem with the motor, a rotor problem, a stator problem, or something like that, that is also reflected onto the system. And motor signature analyzers, very specialized instruments, can detect that and say, well, this signature, you have a rotor problem or whatever. Okay, so they're unique, that they're also can be affected negatively by harmonics, but also cause harmonics as a diagnostic that we can use for diagnostic information to see if something's not operating properly with them. So it's part of the maintenance of motors, I guess, is the point. Products like the Dranets, portable, in fact, our fixed systems, are used to manage the harmonics in the system, both at the terminals of motors and other loads, but also at the point of common coupling and with the utility system to look at the effects on the entire system. So we teased you before, I mentioned this before, about the energy savings lighting or the energy saving light bulbs. Are there power quality concerns? We shared this wave shape with you towards the end of last week's power quality presentation. And for those of you who don't recall or didn't attend, What you see in red here is an incandescent bulb, and ignore this distortion. This is actually probably from the bench in our lab out here, just what's going on in the power system. But here's a compact fluorescent bulb, almost looks like a switch mode power supply, and that's in green. And in blue is the LED bulb. This is the current drawn by these light bulbs. So you look at it a little bit different. Here's the current spectrum from Dranview, but it's really simplified down here in the left. So with the incandescent bulb, the current THD was 3.6%, but it was drawing a half an amp. Okay, that was that 60-watt light bulb. All right, and I would argue that this really isn't 3.6% from the light bulb. It just had distortion on the power system there. You look at the compact fluorescent bulb, you can see the current THD is 90% or higher. And earlier generations of these light bulbs were well over 100% current THD. But it is consuming much less electricity. It's 150 milliamps or 0.15 amps. So we look at the LED bulb, its harmonic content, they've improved the technology from the CF bulbs, is just under 15% at 14.5%. So much better when it comes to harmonics, but you see even the power consumed is even lower at 80 milliamps. If you recall from Thurman's energy presentation in the 26th, we had a trend of the power consumption, which of course the incandescent was the highest, but that trend demonstrated the reduced energy consumption on the CF and the LED bulbs. And you see that represented in these current draw numbers right here. So to wrap this up, and again, this is the entire case study, the energy savings light bulbs tested did deliver the energy savings. However, the CF bulb was very rich in current harmonics. However, in reality today, there aren't as many of them out there because most of us have transitioned to LED bulbs, although I'm sure people, including myself, do have some CF bulbs. The LED bulb was still distorted, current harmonics, but it's still, it's much better, only at about 14.5%. So back when we started to use these and the U.S. government changed the requirements and forced the manufacturing to end of most incandescent bulbs, the popularity of the CF bulbs was the basis for utilities' concern and interest in the mass deployment and of these energy savings lighting. And what they were concerned about, it's not if in your home you have one CF bulb or maybe even now today with an LED bulb, they were concerned about, okay, you replace every light bulb in your house with CF, a bulb, and every house in your neighborhood and every house on that substation now has these higher distorted bulbs, these CF bulbs, and now these LED bulbs. There was concern over what the effects on the power system would be, okay? Turned out to be not a really big concern, but the utilities and the academics were saying, well, hold on, you know, what happens when all of us switch to these energy efficient lighting, including businesses now, okay? And the people selling these bulbs and the energy conservationists and those touting the energy savings were saying, hey, listen, you're saving a ton of energy, you're consuming less current, so it won't be as much of a problem. And if you think back when we talked about 5/19/2014, I discussed TDD, total demand distortion. So if you think about it in these very terms, maybe we can make more sense out of it. So when you look at this, and this is using the CF bulb because it's worse, okay? You look at the actual harmonic current drawn are very small for each bulb. So on the CF bulb, the third harmonic was only 70 milliamps. So in our homes, typically in the United States, maybe you'd have a 15 amp circuit or sometimes a little larger 20 amp circuit. So you think of 70 milliamps on a 15 amp circuit, that's negligible, okay? And even if with all your, a lot of lighting on that circuit, it's still negligible. So really, I think that was the reason why it didn't become a big problem, at least here in the United States, because yes, they look worse on paper, but the actual current draw and the distorted current draw was much smaller, okay, than that of a full incandescent light bulb. You know, we're saving 75% of the energy. We're only consuming about 25% of the power that we did before, okay? So, excuse me, the concern was the cumulative effects of the larger number of light bulbs, okay, but it really didn't cause an issue because of this. Okay, so we do have just a few more minutes, so we're going to actually give you that bonus section here, and we're going to talk about some standards for distributed energy resources. It wasn't actually in our our agenda for any of our power seminars or the virtual power seminars, but this is a module, small module, 5 minutes or so, that we have for our full power quality seminars, our in-person seminars that we've done hundreds of in person. So distributed energy resources, or DER, those are wind farms, those are solar farms, whether they be small rooftop things to commercial ones on businesses or these big energy farms. And in the United States, there's a standard IEEE 1547 that is meant to manage the interconnect from these distributed energy resources, or DERs, to the grid. So this is for mostly for safety, where it started many years ago. This standard started in 2003, last updated in 2018, and there's been a couple revisions in between. But the whole point is to focus on the interconnect of the DER device to the electrical power system, the EPS. So it's at kind of that point of common coupling that we're talking about before. So the main purpose was coordination of the DER for safety, energization, and ride-through, but it has evolved for power quality concerns as well. That's why we're mentioning this here in this presentation, because it does wrap into our power quality discussions that we've had, all right? And just note, this is not specific to the type of DER, okay? Wind, solar, anything else, hydrogen plants or whatever would fall into this category, all right? It's based upon the voltage and the available power in basic terms from these DERs. That's what this standard does to give you the guidelines on compliance. Well, the 2018 revision included PQ compliance guidelines. That's why we mention it here, as well as online and offline compliance guidelines, where that says when the DER is operating out of particular limits, it's got to be offline, shut itself off, or the utility can shut itself off. Like the next bullet here, it's the application of smart inverters. Inverters take your solar farm and take your DC from your solar panels and make it AC, invert that into a nice AC 60 hertz or 50 hertz line and connects it to the grid. But these smart inverters can be remotely controlled, and they can be remotely controlled by the system owner as well as the utility system. So when the utility contractually, if they identify a problem with the DER, they can shut it off, or they can use the DER as an asset and increase its reactive power, or do other things to use it as an asset on the power system. And this is all under contract with the owner of the DER, okay? And that goes to the last bullet with communication control. So we're not going to elaborate on that, but that's kind of what this standard covers, and in a modern kind of DER system. A lot of this was based upon Arizona in the United States, California, and Hawaii, which are some of the big alternative energy states due to the sunshine that they get. Well, 1547 outlines several parts that overlap to power quality: DC injection, rapid voltage change, which we haven't discussed, RVC. It's part of 61000-4-30 edition 3. So all of our current products can measure this. And these are just changes, gradual changes in the voltage. They're not dips, they're not swells, they're not sags. These are kind of the voltage changes slightly within the limits of measurement. So it's doing that. That's what rapid voltage changes are. Flicker, not unlike rapid voltage changes, it's kind of high current loads can cause flickering, very short-term changes at a kind of a sub-harmonic rate, maybe at 10 hertz or at 12 hertz, it distorts the waveform. It also, 1547 looks at the harmonic current, over voltage, and the overall power quality at the interconnection of the grid. All right, so just spending a second or two on each one of these. DC injection, just keep in mind that a lot of the alternative energy like solar DC systems, so they look for the DC component. They want to manage that being injected into the grid. Rapid voltage change is what I saw before. These are said before, these are the operating limits in blue here for the power system, and these are changes within those operating limits. That's what rapid voltage change is. More of a European concern, an international concern outside of the United States. Flicker I mentioned before, that's that PST and PLT, short-term flicker, long-term flicker. They gave statistical requirements for that. These are things that are measured by any product that's IEC 61000-4-30 Class A, Edition 3 compliant, as well as the harmonics. These are the harmonics that we spoke about before. That's why I threw in this session that it's based upon 519-2014 limits is what they put in, as well as over voltage limits as well that they put into that. All right. So really what is needed, and this is kind of a newer technology on how to measure the power quality compliance of this DER kind of system. And we see a future in this, that interconnection point, especially when the utility, based upon modern contracts and smart inverters, may have the ability to control the owner's system. So the utility uses a third-party private system as its own resource. So we think that there's more in the future, is measuring the PQ aspects of the interconnect. So the utility makes the decision to take a system offline. Well, maybe something needs to validate that that was a true decision. You know, maybe there was power quality problems or harmonic issues, and the utility shut off a DER as a result of that. We know that happens today, but it's just not automatic. We've been involved in wind farms where the utility wants to shut off the wind farm because it's generating too many harmonics. There's an issue with it. Okay, so there's definitely a future in the monitoring of this. And these are some of the points that we see that are going to be monitored. Of course, the generation and distribution systems. Right over here is that M is where the DER interconnects to the grid. But we also have end user systems, because end users, just maybe a factory or whatever, may have their own alternative energy. So the site is not dedicated to alternative energy like here, such as a complete wind farm or a solar farm, but the customer here, who may be a manufacturing plant or an office building, may have DER as well. So it's managing that that interface. So anyway, we see these as future potentials. We know our tools are being used reactively now for these applications. We know our fixed tools are being used proactively for that at this moment, okay, to manage this relationship between utilities and the DER owners. So we just see a larger future, and that kind of wraps up all of our power quality monitoring standards that we see indirectly related to the monitoring instruments. So we're going to wrap this up right now. We are done. Thank you very much. And then we're going to get to your questions. But I do have one final poll that I do want to share. First of all, before I launch this, I want to thank everyone for attending our web presentations to date. Again, we do have one more. That's a week from today, when we talk about how to do a power quality survey. But we want to get your attention here and ask, well, what do you think? You know, what have we done right? What would you like to see more about? So this is a two-part question, if you guys don't mind giving your opinion on. So have you found these web presentations or web power monitoring seminar series to be useful? And we are also planning our next round. We're going to take a little break here. Sometime in October, maybe early November, we're going to come back with more trainings. We're brainstorming now on what that training may look like. So we have some questions for you on what you would like to see in the future. So this question too, just remember, it's a multiple choice question. So check off any of those that you like. So would you like to see more power monitoring education? Dranet's portable instrumentation operational training, Dranet's fixed instrument operational training, Dranet's software operational training, more product information training, or product application information, which is the last one. So how to use our products in particular applications. So that's what that's meant to be. So we'll let it go for another couple seconds, and then we'll share the results of that. And then of course we'll get to your questions. So let me cut this off right now. Let me share the results. And well, first of all, thank you so much for the positive feedback and the yeses on question number one. We greatly appreciate that. We think these have gone quite well, but it's not necessarily what we think, it's what our users think. And this is resounding yes, so thank you. And we're going to take this information in number two here and use that accordingly as well. So we hear you, and we see a very strong Dranet's portable instrument operation training request here. We started our web presentations in the just when COVID started in May and June with that very thing, as well as our software training. So we see we have a request, an indirect request here for more of that. So you know, thank you. If you do have additional suggestions, please chat them up. We're happy to take care, to answer them and to take them into our planning. And also send me an email, send Ken Thurman an email, or whomever. So. Okay, let's get to your questions. Thank you very much. Let me stop sharing these results. Ken, can you close that out for me, please? Thank you. Okay, so let's look at the chats here. All right, I'm going to stop top top down, and Ken Thurman, if you could help me, please. From Jay, was that Grandview Harmonics report with the pass-fail a snapshot of time? The answer is yes. Yes, it was from Grandview. No, it's not a snapshot in time. If you were referring to the IEEE 519 2014 report, it's a summary over one day, as well as another report that's done for the entire week. Okay.
Yep, confirmed.
Okay.
Daily compliance, weekly compliance. So that's confirmed. That's correct.
Okay. All right. Thanks, Thurman. He could tell me if I'm wrong. If he says I'm wrong, I'm wrong. So I'll listen to Thurman. So anyway, okay. Why was ITHD used in the case study instead of TDD? One of the reasons why this was not on any particular circuit. This was just looking at the pure harmonics generated from those light bulbs. This was not on a 15 amp breaker in your home or something in an industrial environment. So that's why ITHD was used in the case study, because we're looking at the raw harmonics that are produced by each of those devices. So can we get your slide deck? We're not sharing our slide decks right now, Michael, but go look maybe later today, maybe tomorrow, depending quite honestly on my schedule, but we will be posting this web presentation as a YouTube video, so you can get the information from there. Okay, so why do you specify 16 hertz and 25 hertz test frequency on an HDPQ? This is from Johan. Johan, can you chat up? I don't really understand your question here. Our HDPQ family can measure at 16 and 25 hertz, so we do tests for that. And but I'm not quite sure your question. So yeah, those are railroad frequencies, as Ken mentioned. I think Thurman's confirming here.
We've had this is Thurman. We've had a number of applications with transportation companies in which HDPQ was used to monitor. We see here 25 hertz, 20 hertz, the rail frequencies. So it was used in those type of applications. So that's the answer to that.
Okay, thank you, Thurman. All right, next question from Ron. Will the session on the 26th talk about how to look at harmonics on a VFD? No, not specifically, Ron. Or Thurman specifically is gonna talk about the systematic steps on how to do a power survey. Specific to a VFD, there's really not much different than you look at. It's not how you look at it, it was how you interpret that information and whether it's an issue. So you know, maybe during one of our next either Grandview and or instrument application things or presentations, we could look at specific loads, and that's what we're talking about in our brainstorming. So as a, you know, not as a product operational training, but as a application training, and what would be the best setup or how to properly set up for use on a in a data center, on UPS commissioning, on VFD troubleshooting. Maybe we will have some sessions on applications and how to apply our tools for those. Maybe our HDPQ Plus family or something like that.
Ron, you and I have spoken a number of times. If there's something that you want to talk about offline, I'll be more than happy to have a discussion with you on that. I do have some insight on that. So just reach out whenever it's convenient for you.
Okay, thanks, Thurman. Yeah, and that's for anyone, of course. You can certainly reach out to us. That's what Ken and Thurman and our tech support are here for. So William asks, I was recently measuring a farm in Virginia, I think, and noticed significant flat topping in the voltage waveform at the mains of the 400 amp. Possible cause. That's usually switch mode power supplies. Switch mode power supplies have kind of like a pulse. Really linear power supplies that are transformer based, they consume current in a nice sine wave. Switch mode power supplies, it's kind of like charging a capacitor, the way they kind of work. So they go along, the capacitor's charge somewhere in the middle of the first half of the cycle, at around the quarter cycle mark, they need to charge that capacitor. So they pulse, they draw current for a very short period of time, stop, and then they do that same thing at that same point on the negative half, about 3/4 into the cycle. So you see those pulses, the flat topping, it kind of pulls down the peaks of the voltage. So there's a fairly large current where that power supply is drawing energy, and it kind of pulls down or flat tops that voltage. So you'll see that when computer equipment is there, computers, copy machines, things like that. So maybe on this farm, some of the loads that are plugged in would have some of those similar characteristics. So ECF, whomever that is, where can we watch previous modules, especially module 3, was not able to attend? They are on, go to dranitz.com. In fact, let me share that right now. And so everyone can see that. Hang on, something I have to do is, just bear with me. I need to open my web browser. I apologize. And let me just quit my PowerPoint. Just bear with me 1 second. Let me open my web browser. I closed everything out before our presentation, so just give me a second here. Let me share my web browser right here, and I am going to load dranitz.com. Hopefully load dranitz.com. Hello. Okay, here it comes. Sorry, just a little slow. Ironically, our website is slow in our building. It's not hosted here. So, okay, so where are these? If you go under support, under Dranitz webcasts, you will see all of our web series that we've just done. So this is loading up over here. Just give me a second. So if you scroll down these images, and it's going to preview the YouTube. So here's our August 5th, August 12th, August 26th, September 9th. And we'll do today's. This will pop down below there. So any of our previous ones, I think it said the 3rd, which is August 26th, that is posted as, it's on our YouTube channel, but our website is sharing our YouTube channel here, okay, is what it's doing. So, okay, hopefully that answered your question. Ron, again, didn't realize that question 2, scroll down, would like to see more using the instrument in specific applications. Yes, thank you, Ron. Yes, we that is a good suggestion, and I think we're going to be doing that as well. So, and if all of you can suggest what applications you think. So either chat up here, drop us a note, an email, a smoke signal to tell us, well, what applications are important to you. But I will also ask that we get our best application information from you, our customers. And so we love when you guys share data from us. Most of the data shared is when people, have questions about how to use the instruments, but we love real data shared from the field. And that helps us do our training, and we reflect that back onto you folks. So, so please share your application information. So okay, from ECF, what is the application of very short and short time? I think you're referring to, excuse me, the Harmonics for 5/19/2014. Basically, it's not necessarily the application like in industrial application, servers or what type of facility. It's more just how the data, the time periods in which the data is collected that the IEEE has defined. So again, 3 seconds for very short time, 10 minutes for short time. The very short time are all accumulated at a 3-second rate into one daily report, as Thurman mentioned before. And that's the very short time. The short time is in a weekly report. Then there's also other reports that go along with that. That's defined in 5/19/2014. I unfortunately cannot supply that standard to you. It's all copyrighted, of course. So you guys can Google that, find our own application notes, go to dranitz.com, look at our application notes. We do have an application note on Harmonics, but also there's other references on the internet for that. So, okay, Johan, I'm glad that answered your question. Thank you. ECF, what is the utility meter used for power factor? Is it displacement or true? Most of the time, the utility meters are true power factor. And for those of you who don't know the difference, true power factor is what it is. It's watts over VA and includes all the harmonics and distortion. So this is a very pertinent topic for harmonics. But displacement power factor is the power factor of the fundamental. So it only includes that 60 hertz or 50 hertz component. But my understanding is most power meters or energy meters are true power factor. The utility meters would use that. Meters like ours and energy meters that are also used for power quality meters, not revenue per se, although some of them may have this, can present both displacement and true power factor. So, but when you only see one thing, power factor, odds are it's true power factor that they're referring to. And Elaine or Alon, I apologize if I'm not pronouncing that right. Is there a guideline on how to select an extra noise filter if harmonics generated by the inverter are too high? Not that I'm aware of. We are more in the test and measurement side, not on the mitigation side. So we're not the appropriate folks to do that, to answer that question. But what I can tell you is that one of the reasons for that harmonic demo tool that you saw is not only for the educational purposes that we mentioned before, but you noticed how you can tune in or out various levels of harmonics. So what people can use this tool for is, and by the way, if you open up a data file, you select a waveform in that data file in DranView, then you open the harmonics demo tool, the harmonics have the harmonic content of the waveform in that file. So it starts with the harmonic rich waveform. So if you apply a filter that's going to reduce the content of the fifth by X%, the third by Y% or whatever, you can reduce that in the harmonic demo tool and use those equalizer sliders and change it. So you could say, in theory, I'm going to put this filtering or harmonic mitigation in my system and use DranView to visualize that for you. Look at the effects on the neutral. So it's not a mitigation design tool, but it can affect you, it can help you look at and judge the effects of that mitigation on your power system, what it could potentially be. So from Jay, do you have a YouTube on DranView software? Not at the moment. We may have a promotional one from a couple years ago, but Jay, if you're referring to operational training on DranView, no. Unfortunately, when we did our May and June presentations, our recordings did not come out properly. The tool, the Join Me tool that we were using, didn't meet our expectations in the end. That's why we changed to Zoom. What we're actually, quite honestly, thinking of doing is repeating some of those because they were very well received, some of those same training, and DranView was included in that. So if we repeat that in the fall of this year, we'll certainly have those recordings available. Then they'll be added right to this webcast page that you guys see. So from Ehrlich, I apologize again if I'm not pronouncing that properly and off topic. Can I ask, what is the minimum percent current of a flexible current transformer rating? Is at 10% to get a correct reading? Yes. We use that as the reference, or let me put this differently. As a reference for all of our CTs, our clamp, our flex CTs, the specified range is from 10% to 100% of full scale. So on your flex example here, if I have my flex CT, a 3000 amp flex CT in the 3000 amp setting, we will specify that down to 10%, 300 amps, all the way up to 3000 amps in that 3000 amp switch setting. So for the flex only, yeah, for that one. Again, it's 10% to 100% of full scale. Same thing for our TR2500 clamp CT as an example. So that would be 50 amps to 500 amps because that's a 500 amp CT. So hopefully we answered that. Devendra, thank you so much for the positive comments on the presentation. And I think that's it right now for the questions. So it's about 17 after 12 our time here in New Jersey. Thank you so much for attending. Ken Thurman and I will hang around here for the next few minutes and answer any additional questions that you have. Again, our next presentation on how to do a power quality survey from Thurman will be doing that. Will be next Wednesday, September 23rd. And again, if you have not registered, we'll pop up the, since we have our webpage here, go to services, product training, and I'm sure most of you have been there, and you will see there's our register now button. And this is the seminars right here. The presentation is right here. So there's the description. So thank you so much. I'm going to mute now. Again, we'll be monitoring your chats. Thanks so much.